Today, we're going to discuss in detail the properties of eigenvalues of bilinear forms. We saw that every symmetric bilinear form on Rn may be diagonalized in an orthonormal basis. This means that there exists an orthonormal basis B, which is U1 through UN, such that the matrix of the bilinear form becomes lambda 1, lambda 2, lambda n. So this becomes a diagonal matrix D, which means that the values of this bilinear form Ui with Uj is equal to lambda I if I is equal to j, and 0 if I is not equal to j. Today, we're going to work with bilinear forms on Rn, but everything that we say today equally applies to Hermitian forms on complex spaces. If we take a vector v with b coordinates being x1, x2, xn, then the quadratic form corresponding to this bilinear form can be written as, so q of v will be lambda 1 x1 squared plus lambda 2 x2 squared plus lambda n xn squared. What we saw in our previous lecture, that orthogonal change of basis. So when we change basis from one orthonormal basis to another orthonormal basis, preserves the eigenvalues of the matrix of a bilinear form. But non-orthogonal change of basis does not preserve these eigenvalues. Let us consider a simple example. So let us rescale our basis vectors. So this means that let's say that Vk is Ck times Uk, where Ck are some non-zero real numbers. So we get a new basis B prime, which is V1 through Vn. So what will be the matrix of this bilinear form in this new basis? So for this, we need to calculate what is Vi with Vj. And so clearly, this will be still 0 if I is different from j. But when I is equal to j, so then we are calculating Ci ui with Ci ui. And so this will be Ci squared times lambda I. So this is if I is equal to j. And what we observe is that the eigenvalues in this new basis will change. What does not change under the rescaling is the sign of the eigenvalues. And this motivates the following definition. The signature of a symmetric bilinear form on Rn with matrix A is a triple of numbers P, Q, and R, where P is the number of positive eigenvalues of A. Q is the number of negative eigenvalues. And R is the number of zero eigenvalues. And clearly, so P plus Q plus R is equal to N. We're going to prove the following theorem, that the signature of a symmetric bilinear form on Rn does not depend on a choice of a basis. So when we change a basis in Rn, the matrix of the bilinear form will change, and the eigenvalues of this matrix will also change. But the signature of the eigenvalues of the matrix of the bilinear form will be preserved. In particular, we see that the bilinear form is positive definite if and only if, so it has the following signature. So P is equal to N, and Q and R are both 0. So that the corresponding quadratic form is diagonalized with positive coefficients. We will begin our discussion by looking at the value of R, the number of 0 eigenvalues in matrix A. We give the following definition. The kernel of a symmetric bilinear form is the following subspace. So let's call it W, which consists of all vectors W in Rn, such that for every U in Rn, the value of the bilinear form UW is equal to 0. We have the following lemma. Let we have a bilinear form with matrix A. Then its kernel W is the null space of A. Let's give a proof. The value of the bilinear form on vectors U and V is given with this matrix as U transpose times A times V. So if V belongs to the null space of A, so this implies that A times V is equal to 0, and thus for every U in Rn, we'll have U transpose times A times V is equal to 0. So this means that V is in the kernel of the bilinear form. And for the converse, so if V belongs to W, this means that for every U in Rn, the product of U transpose with AV is equal to 0. In particular, this means that AV transpose with AV is equal to 0. But for real vectors, this happens only when the vector itself is 0. So AV is equal to 0, and which implies that V belongs to the null space of A. And so here we prove that every vector in the null space of A belongs to the kernel of the bilinear form, and every vector in the kernel of the bilinear form belongs to the null space of A. So these two spaces are the same. As a corollary, we get that the value of R is equal to the dimension of the kernel of A, which is dimension of the kernel of the bilinear form. And thus, R does not depend on a choice of a basis. So indeed, so R is the number of 0 eigenvalues of a matrix A. So it becomes the dimension of the eigenspace of A that corresponds to eigenvalue 0. But the 0 eigenspace of A is precisely the kernel of A. And by this lemma, the kernel of A is the same as the kernel of the bilinear form. But the kernel of the bilinear form does not depend on the choice of a basis, because we defined the kernel of a bilinear form purely in terms of the bilinear form itself and not in terms of matrix A. And thus, the value of R does not depend on the choice of a basis. We give another definition. A bilinear form is called non-degenerate if its kernel is the 0 subspace. And we see that a bilinear form is non-degenerate if and only if the value of R in the signature is equal to 0, and this happens if and only if the determinant of the matrix of the bilinear form is non-zero. If the determinant of a matrix is non-zero, then all eigenvalues are non-zero, and then the value of R is equal to 0. We recall that the determinant of a diagonalizable matrix is the product of its eigenvalues. So the determinant is non-zero whenever all eigenvalues are non-zero. And so this means that if we have a non-zero determinant of the matrix of a bilinear form, then R is equal to 0, and the bilinear form is non-degenerate. Let us look at the structure of the degenerate bilinear forms. We have the following proposition. Let we have a bilinear form on Rn with kernel W. Then we get a non-degenerate bilinear form on the quotient space. So Rn quotient by W defined by the following, that if we take two cosets, U plus W, with v plus w, then this is defined as the bilinear form uv. So we're in the right-hand side, we take a bilinear form on Rn. To prove this proposition, we need to show that the value of this bilinear form does not depend on the choice of a representative. If we take two representatives of a coset, so u1 plus w is equal to u2 plus w, and v1 plus w is equal to v2 plus w, then we need to show that the right-hand side of this equality will be the same. So this means that u1 with v1 is equal to u2 with v2. But these equalities imply that there exist w prime and w double prime in the kernel such that u2 is equal to u1 plus w prime and v2 is equal to v1 plus w double prime. Then we will get that u2 with v2 is equal to u1 plus w prime with v1 plus w double prime. And then expanding, so this will be u1 v1 plus w prime with v1 plus w double prime plus u1 with w double prime. But here w prime and w double prime belong to the kernel of the form. So this means that this is going to be 0 and this is going to be 0. And so we get that this is equal to the value of the bilinear form on u1 and v1. And this means that this definition is well defined. Verification that this new form on the quotient space is symmetric as bilinear is straightforward, and I leave it for you as an exercise. Now let us show that this form is non-degenerate on the quotient space, on Rn quotient by w. Well, suppose we have some coset v plus w is in the kernel. Then this implies that for all cosets u plus w, we have that the value of the bilinear form u plus w with v plus w is equal to 0. But then from this definition of the bilinear form on the quotient space, we see that this means that for all u in Rn, the value of uv is equal to 0. So this means that v belongs to the kernel of our original bilinear form. And this means that the coset v plus w is equal to the 0 coset. And we see that the only vector which is in the kernel is the 0 vector in the quotient space. Let us state a second proposition, which is closely related to the first one. So we have the following. So again, let we have a bilinear form on Rn with kernel w, and let U be a subspace in Rn such that we have a decomposition of Rn into a direct sum of W plus U. Then the restriction of the bilinear form to u is non-degenerate. Let's give a proof. So suppose vector z belongs to the kernel of the restriction of the bilinear form to subspace U. This means that Z belongs to U, and for all U in the subspace, the value of the form U with Z is equal to 0. We claim that this vector must belong to the kernel of the bilinear form W. Indeed, let V be an arbitrary vector in Rn. We want to show that the value of the bilinear form V with Z is equal to 0. So this will mean that Z belongs to the kernel of the bilinear form, so it's in W. Since we have a decomposition that Rn decomposes in the direct sum of W plus U, we conclude that there exist vectors little w in W and little u in the subspace U, such that V can be decomposed as a sum of W plus U. But then we can calculate the value of Vz. So this is equal to W plus U with Z. So this is equal to Wz plus Uz. But the first is equal to 0 because W is in the kernel of the bilinear form. And the second one is equal to 0 because Z belongs to the kernel of the restriction of the bilinear form to U. And so the result is equal to 0. But now we obtained that Z belongs to the intersection of U with W. But these two spaces form a direct sum. And so this means that this intersection is a zero subspace. And this implies that Z is a zero vector. This proves that the kernel of the restriction of the bilinear form to U is trivial, and so this means that this restriction is non-degenerate. These two propositions are closely related because this decomposition of Rn into W plus U implies that U is isomorphic to the quotient space of Rn by W. So this quotient space with the induced bilinear form may be interpreted as a subspace U with the restriction of the bilinear form to the subspace. These propositions also tell us that we can reduce the study of degenerate bilinear forms to the case of non-degenerate bilinear forms. Now we're going to return to the proof of the theorem that the signature of a bilinear form is invariant. We state the following proposition. Let we have a symmetric bilinear form on Rn, which is diagonalized in some basis B, which is U1 through Un, with signature PQR. This means that if the B coordinates of some vector V are x1, x2, xn, then the value of the quadratic form on a vector v is going to be the sum I goes from 1 to p lambda I times xi squared minus the sum j goes from p plus 1 to p plus q mu j times xj squared, where mu j's are minus lambda j's and are positive. So we have p positive eigenvalues and q negative eigenvalues. Consider subspaces U in Rn for which the restriction of the given bilinear form to U being positive definite. So this means that for every u in U which is different from 0, the value of the quadratic form on U is positive. Let P star be the maximum possible dimension of such subspace. Then we claim that P is equal to P star. That is, the value of P star is equal to the number of positive eigenvalues in a given diagonalization of the matrix of the bilinear form. We point out that P star is defined purely in terms of the bilinear form and not in terms of a particular choice of a basis or a matrix. Then the equality between P and P star means that the number of positive eigenvalues does not depend on the choice of a basis. To show that Q does not depend on the choice of a basis, we could consider a family of subspaces for which the restriction of the bilinear form is negative definite. And then, in a similar way, we can prove that the value of Q is equal to the maximum possible dimension of such subspaces. Thus, the theorem on invariance of the signature will follow from this proposition. To prove this proposition, consider the span of the first p basis vectors. We point out that restriction of the bilinear form to this subspace is positive definite. Because the corresponding quadratic form will be given just by the first sum, and here we have sum of squares with positive coefficients. So clearly this is positive definite. And then this implies that P star is greater or equal to P, because now we have a p-dimensional subspace with the positive definite restriction. Let us show that P star is equal to P by contradiction. Suppose P star is greater than P, and let us choose U be a subspace such that restriction of the bilinear form to U is positive definite. Consider the following subspace S, which is the span of vectors u p plus 1 through un. we have that the dimension of this space is n minus p. And then this implies that dimension of U plus dimension of S is strictly greater than n. And we have the following fact, that if the sum of dimensions of two subspaces is greater than the dimension of the ambient space, then these two subspaces have a non-trivial intersection. So this implies that the intersection of U with S is not equal to 0. And let V is a vector in this intersection. And V is not 0. Since V belongs to the subspace S, this means that the value of the quadratic form on V is less or equal to 0. So indeed, V is a linear combination of basis vectors from UP plus 1 to UN. So this means that the value of the quadratic form is given by the second term, which is a sum of squares with negative coefficients. So the value of the quadratic form will be less or equal to 0. But V is also a vector in U, and the restriction of the bilinear form to U is positive definite. So this means that Q of V must be greater than 0, because V is a non-zero vector. And then these two inequalities contradict each other, so we get a contradiction. And the source of this contradiction was that we assumed that P star is greater than P. So what we conclude is, in fact, we have equality, that P star is equal to P, and thus the number of positive eigenvalues of a bilinear form does not depend on the choice of a basis. We make the following remark, that the change of basis does not change the sign of the determinant of the matrix of a bilinear form. Indeed, we know that we have the following transformation law for matrices of bilinear forms, that AB is equal to C transpose times A times C. And then this implies that determinant of the new matrix is equal to, when we take determinant of the right-hand side, then determinant of C transpose is the same as determinant of C, and then we get determinant of C squared times determinant of A. And of course, so here we have a change of basis matrix, so determinant of C is non-zero. We point out that for non-degenerate forms, the sign of the determinant of a matrix A is equal to -1 to the power of Q. So it's determined by the number of negative eigenvalues. Let A be a matrix of a symmetric bilinear form. We set delta K to be the determinant of the principal K by K minor of A. Here we take matrix A and take the top left corner of this matrix, formed by the first K columns and the first K rows. And the determinant of this K by K matrix we denote by delta k. We can compute the signature of a bilinear form by computing eigenvalues. However, computing eigenvalues may be an expensive operation. Instead, our idea is that we would like to express the signature of a bilinear form in terms of delta k's. We state the following theorem, which is called Sylvester's criterion. Let we have a symmetric bilinear form on Rn, or a Hermitian form on a complex space Cn with matrix A. Then we make two claims. First, this bilinear form is positive definite if and only if for every k from 1 to n, delta k is greater than 0. And the second claim, assume that all delta k's are non-zero. So delta 1 is non-zero, delta n is non-zero. Then the signature of the bilinear form is given by the following sequence of signs. So we take sine of delta 1, then sine of delta 2 divided by delta 1. Then we take sine of delta 3 over delta 2, and so on, up to sine of delta n over delta n minus 1. Here, in the second part, we assume that delta n is not equal to 0. This means that the matrix has a non-zero determinant, and thus the form is non-degenerate. So the value of R is equal to 0. And then the values of P and Q are determined from this sequence of signs. The value of P is equal to the number of positive signs in this sequence, and the value of Q is the number of negative signs in this sequence. Let us give a proof of part 1. So let's assume that the form is positive definite. On Rn. Then its restriction to subspace UK, which is the span of the first k basis vectors, so U1 through UK, is also positive definite. But then we recall that the matrix of a positive definite bilinear form has a positive determinant, because this determinant is the product of positive eigenvalues. And then this implies that for all k, delta k is greater than 0, because delta k is the determinant of the matrix of the restriction of the bilinear form to the subspace UK. Now, the converse claim, stating that if all delta k's are positive, then the form is positive definite, this will actually follow from the second part of this theorem. If all delta k's are positive, then in this sequence we only have positive signs, and then part 2 claims that all eigenvalues of this bilinear form are positive. Let us now prove part 2 of this theorem. We claim that this bilinear form may be diagonalized in bases v1, vn such that the sign of the first eigenvalue is equal to the sign of delta 1, the sign of the second eigenvalue is equal to the sign of delta 2 over delta 1, and so on, and the sign of the last eigenvalue is equal to the sign of delta n over delta n minus 1. And in addition to this, for every k from 1 to n, we have that the span of the first k new basis vectors in which the form is diagonal is the subspace uk, which was the span of the first k basis vectors in the original basis. We're going to prove this by induction on n. And the basis of induction is obvious because 1 by 1 matrix is diagonal and lambda 1 is simply equal to delta 1. The idea of the proof is to use Gram-Schmidt procedure. Gram-Schmidt procedure, as we previously have discussed it, allowed us to take a non-orthonormal basis of a subspace and convert it into an orthonormal basis of a subspace. Here, we will do the opposite. We may start with an orthonormal basis of Rn, but in which the matrix of a given bilinear form is non-diagonal, and then convert it into a non-orthonormal basis, but in which the given bilinear form diagonalizes. What is our induction assumption? So we have a basis v1 through vn minus 1 of the subspace un minus 1 with the property that vi with vj is equal to 0 if I is different from j, and it's equal to lambda I if I is equal to j. And so here I and j are from 1 to n minus 1. And the signs of these eigenvalues satisfy our property that the sign of lambda 1 is equal to the sign of delta 1, dot, 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 and the sign of lambda n minus 1 is the sign of delta n minus 1 over delta n minus 2. And in particular, the eigenvalues lambda 1 through lambda n minus 1 are not 0. Now we need to construct the last basis vector Vn. We do this using the Gram-Schmidt formula. So we said that Vn is equal to un minus v1 with un over v1 with v1 times v1 minus v2 with un over v2 with v2 times v2 minus vn minus 1 with un over vn minus 1 with vn minus 1 times vn minus 1. Now, in denominators here in this formula, we have lambda k's, and these are non-zero scalars. Let us check that this will diagonalize the bilinear form. So we need to calculate vk with vn. this will be the following. So for Vn, we substitute this long expression, and then we get Vk with Un. And then when we take the value of the bilinear form of Vk with one of these terms, so we get mostly zeros because we have that Vi with Vj is equal to 0 when I is different from j. So the only term that we need to take is the term with Vk. And then we get minus Vk with Un over Vk with Vk times, and here we take the product of Vk with Vk. And we see that denominator will cancel, and we get 0. This proves that this bilinear form will diagonalize in the basis of V's. Then we set lambda n to be the value of Vn with Vn, and then we see that the matrix of the bilinear form in basis V1 through Vn is indeed diagonal. We have observed that the change of basis does not change the sign of the determinant of the matrix of the bilinear form. The sign of the new determinant is the sign of the product, lambda 1 times lambda 2 times lambda n, because the determinant of a diagonal matrix is the product of the diagonal entries. But the old determinant was delta n, so we get that this is the sign of delta n. Now let us separate the left-hand side as the product of sign of lambda 1 through lambda n minus 1 times the sign of lambda n. And then by the induction assumption, so if we multiply the first n minus 1 signs, then we see that this is simply becomes sign of delta n minus 1. So we have that the sign of delta n is the sign of delta n minus 1 times the sign of lambda n. And this gives us the desired result, that the sign of lambda n is equal to the sign of delta n divided by delta n minus 1. And this completes the proof of Sylvester's criterion. In the statement of Sylvester's criterion, we required that all determinants of principal minors, delta k's, are non-zero. For small values of n, we can determine the signature of a bilinear form even if this condition fails. So let us give some examples. So suppose we have a bilinear form with the following matrix: 0, 1, 1, 2. So here we have that delta 1 is equal to 0, and delta 2, which is the determinant of this 2 by 2 matrix, is minus 1. Here we have the determinant of A, which is delta 2, is not equal to 0. So this means that this form is non-degenerate. And in particular, the value of r is equal to 0. Thus, we have two non-zero eigenvalues. So what are their signs? So we know that the sign of delta 2 is the product of the sign of lambda 1 times the sign of lambda 2. But this determinant is negative. So this means that one eigenvalue is positive and another must be negative. So this implies that p is equal to 1 and q is equal to 1. Let us consider a second example. So let A be the following matrix of a bilinear form: 0, 1, 2, 1, 0, 1, 2, 1, 0. Here we have that delta 1 is equal to 0, delta 2 is equal to -1, and if we calculate the determinant of a 3 by 3 matrix delta 3, then we can easily see that this is equal to 4. Since, again, delta 3 is non-zero, so this implies that the form is non-degenerate. So all eigenvalues are non-zero. And then the product of the signs of these eigenvalues is the sign of delta 3, which is +1. This means that either all 3 eigenvalues are positive, or there are 2 negative eigenvalues and 1 positive eigenvalue. But we see that this bilinear form is not positive definite. By the first part of Sylvester's criterion, a positive definite bilinear form must have all positive deltas. This implies that some of the eigenvalues are negative. And so the only possibility here is that we have signature with p is equal to 1 and q is equal to 2. Now, let us explain. Why do we care about positive definite, bilinear, and quadratic forms at all? For this, we are going to discuss a natural application of this theory to calculus. Let us recall the second derivative test. So let f be a twice differentiable function from R to R. Let x equals a be a critical point for f. So this means that f prime at a is equal to 0. 1. If the second derivative of f at a is positive, then x equals a is a local minimum point. And if the second derivative at a is negative, then x equals a is a local maximum point. So here, if the graph of this function is concave down, so that is the second derivative is negative, then this point is going to be a local maximum. Next, we want to generalize this to the multivariable setting. Let f be a twice differentiable function from Rn to R. What does it mean? So this means that we have the following Taylor expansion, that near the point x equals a, so we can write f of x is equal to f of a plus the linear part, so we have the sum k goes from 1 to n, the partial derivative df dxk evaluated at a times xk minus ak, right? So where a here is the point a1 through an, and x is a multivariable notation x1 through xn, plus the quadratic part, which is 1/2 sum I goes from 1 to n, and j goes from 1 to n. So we take the second derivative of f with respect to xi and xj evaluated at a times xi minus ai times xj minus aj, plus the tail, which is little o of the distance between x and a squared. A function is twice differentiable if it has the following approximation near the point A. If we introduce the displacement vector v, which is x minus a, so this is a vector x1 minus a1, dot dot dot, xn minus an, then we see that we can write this approximation as f of x is equal to f of a plus the first derivative terms will be a linear form of a vector v, and the second derivative terms will be a quadratic form on a vector v plus little o of the length of v squared. Then a necessary condition for x equals a to be a local maximum or minimum is that L of v must be equal to 0. So this means that for all k, the partial derivative df dxk at the point A all must vanish. From this Taylor expansion, we see that the second derivative of f is nothing but a quadratic form. With matrix B, where Bij is the matrix of partial derivatives. So we take the second order partial derivative of f with respect to xi and xj evaluated at point A. And now we can state the second derivative test. Let A be a critical point of a function f from Rn to R. So this means that for all k, first partial derivative df dxk at point A are equal to 0. 1. If the quadratic form q of v of the second derivative of f is positive definite, then x equals a is a local minimum point. If q of v is negative definite, then x equals a is a local maximum point. And 3, so if q of v has both positive and negative eigenvalues, then x equals a is neither a local maximum or a local minimum. And this is a so-called saddle point. So in some directions, this function is going to be increasing, and in other directions, this function is going to be decreasing. So for the study of local maxima and minima in the case of multivariable functions, we need to know when quadratic forms are positive definite. And for this, Sylvester's criterion may come very handy.